So in my last class I was explaining this, that is the second phase of this rotatory motion, and here the second phase of the rotatory motion consists of angular momentum and conservation of angular momentum, and thereafter it is energies and velocity, time, acceleration of a rolling body down that inclined plane. So in this second phase already we have completed that necessary theory, and again after that we have solved some more problems also. So in this case we are coming to that, we continue those problems. Now we are coming to that seventh problem. Already we have completed that I think 6 of those problems. Now it is the seventh problem. A cockroach of a mass m is moving on the rim of a disc of rod r, disc of radius r with a velocity v in anti-clockwise direction. The moment of inertia of the disc about its natural axis is I, and it is rotating in a clockwise direction with angular speed omega. If a cockroach stops moving, then what is angular speed of the disc? That will be. So again this problem is also based on conservation of angular momentum. So we are taking, this is a disc is here and it is rotating about its natural axis. It is rotating about its natural axis. A cockroach of a mass m is moving on the rim of a disc of radius r. So that's why this is taken, r is here. We can take it as a small r, and again this particle is, so this mass is there, and that you are given this value of this cockroach is the mass is small m is there, and here this cockroach of a mass m is moving on the rim of with a velocity v in anti-clockwise direction. So that's why in anti-clockwise direction means this cockroach is moving like this, whereas moving like this, the mi of the disc about its natural axis is I, and it is rotating in clockwise direction with angular speed omega. So with angular speed of omega, it is rotating in a clockwise direction, and its moment of inertia is directly given, that's value is the I. Its value is the I is given, and thereafter if a cockroach stops moving, what will be that angular speed of that disc? What will be that angular speed of the disc? Here we are applying that I1 omega 1 is equal to I2 omega 2. And here also there is no any type of external torque, only that internal changes. So here first of all that I1 omega 1, what it indicates, that is a total angular momentum when a cockroach is moving in anti-clockwise direction at the rim of that disc. And for that I1 can be taken, this is for the disc, it is taken as the I is here. This is for the disc, it is taken I is here, because you are directly given it is the I, and its angular velocity can be taken omega, that is also given, that disc is rotating with an angular velocity of omega, and thereafter when you are coming to this cockroach, and for that you have to apply that general formula only. That general formula, because it is moving with the speed v, so it is moving with the speed v in anti-clockwise direction. So that's why you are already given that problem with a velocity v in anti-clockwise direction. So that's why you have to apply that general formula for the angular momentum, that is taken mvr. So that is taken mvr. But here this cockroach is moving in anti-clockwise direction, that's why it becomes a minus mvr. So that's why it becomes a minus mvr. So you have to apply that general formula, because already you have the formula for this angular momentum, L is equal to I omega. In addition to that, L is equal to mvr is also there. So that's why here we are applying that angular momentum formula for this cockroach is the mvr. Why that minus sign is coming? Because it is moving in this direction. So it is a minus mvr is there. And thereafter I2 means here this in this second case. In this second case means in that second case the cockroach has stopped its movement. So now it is only that disc is rotating with angular velocity as usual. For that it will be I omega. For that it will be I omega, and thereafter it is a cockroach has stopped means, and for that what you have to take, it is its moment of inertia. For that cockroach is, it is the general formula, mass into distance square. Mass into distance square means it is taken mr square to be taken, and both of them are having that angular velocity omega dash. So it is omega dash. So in this case it is taken I omega, and thereafter it is mvr minus mvr, and thereafter it is I plus mr square omega dash is here, and the common angular velocity when the cockroach stops its movement, then omega dash is equal to I omega minus mvr by I plus mr square. I plus mr square is here. So its value is that's value is the I omega minus mvr by I plus mr square is here. So once again I tell you this problem. Here just a little bit of confusion is, here this cockroach is moving anti-clockwise direction, whereas this disk is rotating in clockwise direction. That is only a slight difficulty is here. So for that you have to change that directions also like this. For that disk it is I omega is there for the disk, and again for that cockroach you have to take the minus mvr because both are mutually opposite, minus mvr, and here I2 is that is I only, and here it is nothing but the I, so only that I, not only that I, and again it is mr square is also there, mr square, because this cockroach is nothing but an object, for that the moment of inertia is the general formula, mass into distance square. So that's why mr square is here, and they are having that common angular velocity. That common angular velocity is becoming like this. So it is omega dash is equal to I omega minus mvr by I plus mr square. Now here that seventh problem is completed. Now we are coming to this eighth problem. So this is seventh problem. This problem is purely based on this conservation of angular momentum. Now we are coming to that next problem. In this problem you are given the angular momentum of a particle rotating about a given center is given by you are given some fill in the blank like this, the product of a mass and its aerial velocity. The angular momentum of a particle, suppose the particle is rotating like this, the angular momentum of a particle rotating about a given center, angular momentum of a particle rotating about a given center. So like this, now it is rotating and it makes an angular displacement d theta, and here it is the center of that, and this can be taken, it is rotating means this will be the radius r is here, and here it will be taken, that is a dr. Dr will be a smaller linear displacement on that circumference. So it is a d theta is the smallest angular displacement, r is here, and again the dr. Now you are supposed to prove that the angular momentum of a particle, so angular momentum of a particle, so it is rotating about a given center is given by, now it is angular momentum that is taken as, in this case it is the angular momentum of a particle rotating about a given center is L is equal to I omega is there, angular momentum L is equal to I omega, and here in this case I is nothing but mr square. So that's why m, and again here it is the r square is there, and omega it is given that first equation. It is given that first equation. So once again I tell you, it is the L is equal to I omega, and angular momentum I is equal to mass into distance square is taken. So mr square and omega, that is the first equation. Now the product of the mass and its aerial velocity, we are starting from that angular aerial velocity. So aerial velocity is here, and that is nothing but area by time to be taken here like this. And how to find out this area? How to find out this area means this is just similar to that of a triangle, because here the angular displacement is very smaller. So that's why it is just similar to that of triangle. So that's why that area can be determined like this. So it is area is equal to, that is area of a triangle of BH. So that's why 1 by 2, and B is nothing but a smaller, and H is a dr is here. And dr is nothing but, again we can take that angle is d theta is equal to dr by r. That is angular displacement is equal to arc by radius. So that's why d theta is equal to dr by r, and dr can be replaced by r d theta. So it is 1 by 2 r square d theta is here. That is area covered by that, that is 1 by 2 r square, area covered by that radius vector is 1 by 2 r square d theta. So here area that is taken 1 by 2 r square d theta, and the time it is taken, the very less time, it is a dt. So that's why d theta by dt is coming. So it will be 1 by 2 r square omega. It is the second equation. It is the second equation. So angular momentum is this much and aerial velocity is here. Now we are taking 1 by 2. We are taking 1 by 2, that gives, so in this case, in that 1 by 2, L by aerial velocity is equal to mr square omega and r square omega, that will be cancelled. So it becomes 2m only, because mr square omega is here and r square omega by 2 is here. That r square omega will be cancelled, 2 comes to the numerator, so it is a 2m only. Now that angular momentum is twice the product of mass and aerial velocity. So it is equal to the twice the product of mass and the aerial velocity. L is equal to 2 into mass into aerial velocity. So this is so this is simple question. Here you have to prove that angular momentum of that particle is twice the product of mass and its aerial velocity. And for that we are finding that angular momentum and again that aerial velocity, and we have taken that 1 by 2, automatically this answer comes. Now this problem is also over. Now we are coming to this next problem. So in that next problem it is mentioned a uniform sphere, a spherical shell and a thin ring, all of same radius, are rotated simultaneously from rest so as to roll down a smooth inclined plane. If a sphere reaches the bottom with a speed of 0.2 meters per second, calculate the speed with which the other two reach the bottom. So here, so first of all you are given that uniform sphere that you are given. Next one, uniform solid sphere. Next one is a spherical shell, that is nothing but a hollow sphere. So hollow sphere is also given, and thereafter a thin ring, so that is nothing but a circular ring. Circular ring is here. So all these are three objects, these are the rolling bodies, all of the same radius, are rotated simultaneously from rest so as to roll down a smooth inclined plane. If a sphere reaches the bottom with a speed 0.2 meters per second, so we are coming to this sphere only, and it is 0.2 meters per second. A sphere reaches the bottom with 0.2 meters per second means already we know for the sphere it is a square root of 2gh by 1 plus k square by r square is the general formula, not for the sphere. For any rolling body along that down that inclined plane, it is a square root of 2gh by 1 plus k square by r square is that formula. In this case for the sphere, that becomes Vs is given, its value is given 0.2 meters per second. So that's why it is the 0.2 meters per second. This is the given value. So that's why it is 0.2 is equal to square root of 2gh. And 1 plus k square by r square means, as you already know, the k square by r square for the sphere is, solid sphere is, so it is 2 by 5. So 2 by 5 is taken. Now here on squaring on both sides, it becomes 0.04. It is 2gh and it becomes 7 by 5. So 7 by 5, that becomes, it is 5 by 7 is here. And from that 2gh is equal to, it becomes 7 into 0.4, 0.28, 0.28 by 5, 0.28 by 5, this is the 2gh only, don't find the value of gh, that is not required. So that's why it is the 2gh only, we got this, this is the first equation. So uniform sphere, and for that the value is given, you have applied this formula, and from that we could find the value of the 2gh only in case of that inclined plane for the sphere. And now we are coming to that other objects also, that is spherical shell and again the thin ring. Spherical shell and again the thin ring is here. So when you are coming to this hollow sphere, for that hollow sphere the formula becomes like this, V is equal to square root of 2gh by 1 plus, for the hollow sphere you must have to remember all these values. Why that rotatory motion is considered to be comparatively difficult when compared to that other chapters? Why? Because there are so many number of formula are involving, and you have to get that command on overall on these formulae. So in this case, for the hollow sphere it will be 2 by 3. That is 1 plus 2 by 3 is here. Now for the hollow sphere it is a 2 by 3. You have to remember it is a 2 by 5 is here. 2 by 3, and for that it is a square root of 2gh. In place of that 2gh, what we can apply? It is 0.28 by 5. So it is 0.28 by 5 is here in place of that 2gh. And thereafter 1 plus 2 by 3 means it is a 5 by 3. That is also 5 by 3 is here. Now it can be taken 0.28 by 5 and thereafter 5 by 3. So it is a 3 by 5 to be taken. Once again I tell you, for the hollow sphere, V is equal to square root of 2gh by 1 plus k square by r square. K square by r square, it is 1 plus 2 by 3, it is 5 by 3, 0.28 by 5 already we got here, and we have to apply, this becomes a 3 by 5. 3 by 5 is here, and after solving that becomes a 0.28 into 3 means that becomes 0.84. 84. Next again it is a 25. Then after solving you are going to get that required answer. So that answer comes. Now it is for the hollow sphere. The same process is to be done in case of that the third object, that is for the circular ring. And for that circular ring, again the same method we take. It is V is equal to square root of 2gh by 1 plus k square by r square is here. And for that circular ring k square by r square, for that circular ring k square by r square is 1 only, So you have to remember all these values. Now here it is, how to remember all these values. Now it is in case of the solid sphere, it is 2 by 5 mr square, and in case of that hollow sphere, it is 2 by 3 mr square is there, mr square. And here in case of that circular ring, it is mr square natural axis, and in case of that circular disc, it is 1 by 2 mr square, 1 by 2 mr square. And again when you are coming to this solid cylinder, that also will be that 1 by 2 mr square about its natural axis. And hollow cylinder, again it is the mr square about its natural axis. Now here the coefficients of all this mr square, they become k square by r square. They become k square by r square. The k square by r square of all these objects are 2 by 5, 2 by 3, 1 by 2, like this. So that's why here also for all these 6 rolling bodies, we have taken that is the k square by r square. Here we are applying that value is the, so k square by r square means it is nothing but the quotient of that mr square in that particular rolling body. So in this particular rolling body ring, that is the quotient of mr square is nothing but 1. So that's why you are taking that 1 is here. So it becomes a square root of 2gh. 2gh already it is here. It is 0.28 by 5. So 0.28 by 5. And again 1 plus k square by r square means just now I told it is nothing but it is the 1 plus 1. So 1 plus 1 is here. So it is 0.28 by 10 is taken. And it is 0.028. 0.028. Then you get that answer. So that is velocity of that hollow sphere and again that circular ring on reaching that bottom of that inclined plane. So now this is a problem based on just velocity of that rolling body along that inclined plane. Now we are coming to this next problem.